This will be the second portion of the video with examples about non-separable differential equations. This one's going to be an example of Euler's method. So we have our initial point here. What we're going to do is plug that into our equation for y prime. So y prime at the point 0, 1 is equal to 3. And then we'll write in our equation y minus yo equals m times x minus xo, or y minus 1 is equal to 3 times x minus 0. And then in order, since we're taking a dx equals 1, our next point of interest is going to be at x equals 1. So we'll plug that into our equation, and we get that y minus 1 equals 3 times 1 minus 0, or y equals 4. That means that our next point is going to be 1, 4. So at the point 1, 4, our differential equation tells us that the slope is going to be approximately equal to 12. So again, we're going to write out y minus yo equals m times x minus xo. Now our next point of interest is going to be x equals 2. So we'll plug that in, and we get that y equals 12 times 1 plus 4 over y equals 16. Meaning that with a dx of 1, we end up with y at the point x equals 2 equals 16. Now let's repeat the exact same problem with a smaller dx. So we have y prime equals 3y, again starting from the point 0, 1. The first few steps are the same, and except here, instead of plugging in x equals 1, you're going to plug in x equals 0.5, so that y equals 3 times 0.5 plus 1, or 2.5. So our next point is 0.5, 2.5. Okay, so now at this point, y prime equals 3 times 2.5, or 7.5. And now I'm going to start using a little shortcut where I'm going to have y next equals y initial, or the one that we're looking at now, plus the slope times dx. So like if we're going from 0.5, 2.5 to our next point 1, then our next y value is just going to be the current y value plus the slope that we found times delta x, or 6.25. Okay, now let's repeat that again. Y prime at our new point is equal to 3 times 6.25, or 18.75. So our next y value will be equal to our current y value plus the slope times our delta x, or 15.625. Meaning that our current point now is 1.5, 15.625. Okay, so now to get to our final point, where x equals 2, Just going to do this one more time. Y prime equals 3y, or 3 times 15.625, 46.875. And so y next is equal to y now plus our slope times our delta x. So that gives us a new y of 39, meaning that with a dx of 0.5, we end up with 2, 39, just about 39.0625 to be precise. Now we're going to actually solve our differential equation to see how the two compare. So y prime equals 3y, dy dx equals 3y, dy over y equals 3x, ln of y equals 3x plus c, so y equals c times e to the 3x. Our initial point was 0, 1, so in order to find c, we'll just plug in 0, and so we find that c equals 1, or y equals e to the 3x. And so then you can just plug in x equals 2. That gives you y equals e to the 6th, which evaluates out to be 403.43. And just to get a better understanding of the Euler's method that we just did, I'm going to show this website. Again, we're going back to MathScoop. And so what I did was I put in differential equation equals 3y. The initial point, our delta x, is 1 and our end value of 2. And so if you look at the graph, you'll see we have something like this. And it shows you all of the steps in between, leading to a final value of 2, 16, which is what we found. Now, if I change our delta x to 0.5, then create Euler table, you'll see that our graph is now a bit steeper. And again, at the bottom, they have all of the steps listed that they took to get to the point 2, 39.0625. Now, using our calculator, we can get even more precise and do things that we wouldn't want to do by hand. So, for example, we could go down to 0.1. Let's see what we get now. So we've got an even steeper picture. And at our point 2, we now have a 190 as our final value. We can go even more in detail and go down, let's say x equals 0.02, create the Euler table. And then you'll see that we get as our final value something close to 320, which is close to what we got when we finally solved it the last time. So from this you can see that really you need to choose a very small dx in order to get close, depending on what your differential equation is.